Hello and welcome. My name is Michael Horn, and in these series of videos, we're going to be walking through a four-part problem. And in this first part, part A, we're going to discretize a 100-liter tubular flow reactor into 100 perfectly mixed sections to simulate back mixing, as you can see on the left. And then we're going to simulate and plot in Google Colab the concentration profile along this tube when a rectangular pulse of height 3 moles per liter and width of 1 minute per superimposed on that 1 mole per liter inlet flow of 100 liters per minute. I know that sounds like a lot of different specifications, but like I said, we're going to start this in here. As you can see, I already have the library imported that we've used in a couple of videos before that are going to allow us to do some of these calculations. So without further ado, let's get into it. All right, so as I mentioned before, we have our library in, and we are first going to input all of the variables that we were given. So as we said, n, which is going to be the number of cuts in this tube, which are going to be perfectly mixed and equal, we're going to set equal to 100. And then our total volume, which we mentioned in the problem, is going to be 100.0 liters. Excuse me. Next is going to be our volume per slice. So essentially, since we're taking our volume, which is 100, and we're going to be taking 100 slices, you can assume this to be 1. But for example, what if it was like, our volume was 12,000 and we want 212 slices? Obviously, that would be a little more difficult to challenge or to calculate. So we're going to be this equal to our total volume divided by n, just so we can be more precise instead of just typing 1. And then we want Q, which is our flow rate in. This is going to be equal to also 100. And this is liters per minute. And then our concentration in, which is another given value, is going to be equal to 1. And this is moles per liter. And then our concentration out, which this is what we're going to be actually finding in an array. And the line below this will kind of explain a little bit more. But so every slice, we're going to be looking at the concentration of that slice. So we're going to do NP full, which will help us create this array. This is going to be n, and we want the array to be first n, so it'll show you which slice it's going along with, and then the concentration in that slice. And then we want to look this at different timestamps, and for this example, we want to look at it at 10 different timestamps. So now currently we have all of our variables defined, and we're able to move on to the next section. Okay, so the next part of this is going to be creating some functions. And the first, we haven't worked with these functions yet in any of these videos, and the first is going to be sigmoid, and this is going to allow us to create some random variables within a range that we choose. So it'll be sigmoid x naught equals 0, and we want that width to be equal to 1. Now, we are going to have to return a function, and there we go. Now this return function we want is actually going to be a logistic function, and for that is going to be sp.special.xbit, and then the equation that we're going to use for this is going to be x minus x naught divided by the width, which we already have set. So now the next portion of this will be actually kind of creating a pulse graph. So this logistic function is creating the equation for us. As you can see, this sigmoid and the special xbit, we're going to use these numbers that we get into our equation below that I'm about to show you guys. So we're going to define this as pulse. We're going to be kind of showing you guys what a pulse phenomena is. And to do this, we need x1, x, and x2. And then we also need C1, C2, and the width is going to be equal to 1. Now, C1 and C2, the importance of all these X and C values that I just typed out are because we want to analyze the concentration over a certain period of time. That is the purpose of this. And so this graphing this process is going to allow us to do that. And to do this, we're going to need a actual line to graph, and this is going to be a rather long equation, so I'll explain it as I go. You're going to take your first concentration You're going to add it to that C2 minus C1. And now this is where you bring in what you just typed above. You're going to multiply that by our sigmoid function that we typed above, which is x naught equals x1 now. And then we're going to set the width equal to the width. Now you're going to take all that and subtract away your C2 minus C1 value, multiplied by, again, that sigmoid. You can see the importance of that function above. And this time, x is going to be equal to, sorry, x naught is going to be equal to x2 instead of x1. And the width is going to still equal the width. So now, as you can see, we have our sigmoid function here, our logistic equations here that we then use down here in our pulse to actually be able to graph all of this, and we're able to continue. So now let's actually get into the plotting section, which we have done multiple times before. So we're going to start with x equals np.lin space, and we want this to go from 0 to 10 to 1,000, which is rather large, but rather safe than sorry. And then again, fig equals underscore make subplots, which is going to actually make the subplot, just as a reminder in case anyone forgets. And then we want to make a scatter plot, and the scatter plot is simply going to be made of the values that we already created. So we're going to x equals x, and then y is going to be equal to the pulse. So essentially this is going to see on the bottom x, and then we'll have a line which will be your y, and that will show that pulse. That is what we're looking for. If there are no errors, we'll see. And that pulse is going to be equal to x, and then 1, and then 2, back to 1, 4, and then 0.01. Okay, so now we are clear to run all and see what happens. Let's see if it works. Second. I'm gonna pause. I'm not sure exactly what's happening. Okay, no issues. My computer was just taking a long time to run it. So as you can see, the significance of this 4 right here that I have highlighted, that is why it pulsed up to 4 and straight back down. So as you can see, as you go along, and then as soon as you get to about 1, it's gonna spike straight up, get up to 4. Is that? Yeah. No, wait. Yeah, just before 1, you're going to start to spike up, goes up to 4, and then immediately comes back down. So 1 to 2 is our pulse as we created, and now we are able to move into the next section. So now we are going to use ordinary differential equations to actually simulate backmixing, and then from the backmixing, we're going to be able to analyze the concentration profile. So first, as I mentioned, we need to put in some of these differentials. And to do this, we're going to do define right-hand side. As you can see, everything that we've been learning previously, we are using now, which we have done this before, which is we're going to be having a vector. Don't forget to indent. And then our concentration N is now going to be equal to that pulse that we just created. So pulse, except T now, because obviously with this derivative coming into play, we're going to be looking at things with respect to time. So now instead of, or not instead, but we're now going to be adding in that T time value into the pulse equation. And then we are going to go from 0 to 1 to 1 to 4 to 0.01. And now our C out is this. Do I need to? I know, I'm sorry. I don't need to label it the same as above because this is going to be a different, this C out is going to be different. So this is going to be equal to a vector. And then now comes in our derivative. So the derivative of C is going to be equal to NP dot zeros with our number of iterations, which is going to be N, which we have as 100 right now. And then we also want DC at 0, and this is going to be equal to Q, which was our flow rate in, times concentration in, minus C0 divided by, and then all of this will be divided by volume. And then the final derivative that we're going to take here is dc of 1, 2, however many numbers we want. So just colon and essentially infinity sign. And this equation is going to be Q flow in multiplied by our C value, which will be from 1 to infinity, minus the same thing, but that will be divided by V. These sometimes trip me up. And then we are obviously going to want to return DC. And we will really quickly run this to make sure there are no errors. All right, we got this green check, as you can see, so we are good to continue. So now one of the final steps is going to be actually creating the plotting and matrix creation of this section. So the next thing we are going to do is, like we mentioned before, we're going to be essentially like checking in on this 10 times. We're going to be looking at the values, seeing what's going on. You can make this as small or as large as you want, but for purposes of this, we're going to check it 10 times. Now, we obviously want to t-plot this, and we want to plot the line space that we already made. So np.lin space, and okay, you can see it's suggesting a 0 to 10 to n times n, which is super similar to what we need, except we don't want to multiply it by n at the end, so we can do tab here. But let's get rid of that. That is what we were looking for. And then next we're going to want to res equals, now this comes the integrate part, which will be doing the math for us to help create these matrices. sp.integrate.solve underscore IVP, which we have used this before. And we're going to do the right hand side. 0, 10, C out, which is obviously the values that we've been trying to, find. Method, which is going to be the same method as that we have been using, which is redo. I think I'm saying that right. Redo. I think I'm saying that right. I don't know. It sounds French, but I'm not French, so I don't know. And then we, same as usual, we want dense underscore output equal to true. Let me read over this to make sure this method redo dense out. Yep, okay. And then the last thing we want is the concentration profiles. So we are actually able to see all of the calculations that Colab has done and analyze them. And this is going to be C underscore profiles equals res dot sol, and we want to be getting these values from the t plot. So let's run this to make sure everything's okay. Green check, so we're able to continue. So we have reached the finale of this video. We are going to create this big plot that has 10 lines, and each are going to be pulsing at different times, and this is going to allow us to see, oh, well, where is it pulsing? Is it the beginning? Is it the end of the tube? And Colab is actually going to be nice enough to allow us to kind of pick and choose which lines we look at. So let's start this process, and then you'll be able to see what I'm talking about. So fig equals make underscore subplots. Now, it has to index at the amount of times that we want it to. So for this, the equation is going to be 4t underscore index in range. And this is the variable in times, which we set to 10. So this will show us 10 indexes. And then we will do fig dot add underscore scatter. And this x we equal np dot range n. And the y will equal the actual temperature profile. So this will show us the pulses that we talked about earlier. run it. I do have an error here. I don't know why I typed that in there. Make sub L. Here we go. This is supposed to be plots, not L pots. Now let's run it. I'm going to take a minute to try to figure this out. I'll be right back. All right, so I'll explain to you some of the errors. So the first error I had was that I did not have parentheses here, silly mistake, and so it was not plotting correctly. And then this fig I had was accidentally indented, so it did actually plot. But then the issue I had was this. I had 1. So when I ran it, it looked like that, which is not at all what it's supposed to look like. I missed a little negative here, so we will put that back in. Now, as you can see, this is showing all of them. So as you can see, this first one at 20, it actually jumped up to our concentration of 4 and then starts to go back down. But if I get rid of this one, I'm going to get rid of all these actually, so to show them. So let's look at this one. Sorry, okay, just so you know, trace 0 is like the point of reference. So let's look at trace 1. Here's trace 2, which kind of goes up towards the end. Trace 3 is pretty flat. Trace 4. This is not, okay. Gotta fix something here. This is not correct. Okay, so we're able to fix that. So let's look in here at trace 1. So this trace 1, as we mentioned before, when you get rid of this one and trace 2, you can see trace 3 through 9 are actually, some are getting larger, some are getting smaller, and this trace 3 actually dips very quickly. So as you can tell, as time goes on, all of these concentrations are starting to vary towards the end of the tube, and that is what we're exactly looking for in this problem. So thank you for following along, and I hope you're able to understand.